Hello and welcome back. I hope you enjoyed your little break there. So can you all hear me and see me correctly? Is all okay? So what we're going to do is start moving into, thank you, and getting the yeses there. Brilliant, thank you. So what we're going to do now is start looking at test-driven development. So the first couple of weeks, what we did, a lot of it with you was to give you a whistle-stop tour, which I'm sure you all kind of realised how whistle-stop it was. It was a fast run at the Java language. So what we're now doing is starting to move into the tool set that we're going to start looking at for agile software development. There's a lot of tooling that can be used, and we'll capitalize a lot on that while we start developing apps as we go along. The main thing that we're going to look at the moment is test-driven development. So what I'm going to do today is talk to you about what test-driven development is, and then kind of we look at an example as we kind of get to grips with what exactly it is. So you'll find the pace of this a lot less rushed, hopefully. So we've got a test-driven development circle of life that goes on, and we're going to discuss this on the next couple of slides. So you'll see that there's the test passes, refactor, test fails. We'll go into what all of that is in a few minutes. So the main thing is this guy here, test-driven development. All code is guilty until proven innocent. That is what we are going to go for. That's our mantra at the moment, is it's guilty till we prove it innocent using our automated testing. Anyone familiar with the waterfall development approach? So this is basically a development approach that is very structured. You do your feasibility, then you move into your analysis, and a small bit of overlap in time here. Then you go into your design. So when you finish your analysis, you may be starting to design a bit while you're in analysis, but you're still moving on. Implementation, test. So they're all distinct phases. And then you go into your maintenance. And then, you go back to doing a feasibility to maintain certain parts of the system, to do kind of change requests or whatever it is. So it's a very structured waterfall approach. And this is what it can look like in reality. So at the top here, you've got all the different dates here, calendar dates. So you might go into your requirements phase, and then you might do your design phase, and then you start doing your coding. And the test, if we look at the test here, the test comes after coding. It can be done in a block. The traditional one is how it's written out. And if anyone has ever coded in this waterfall approach, this is where you start going into a real cycle of test fix, test fix, test fix, test fix, and so on. Also, working features. We're concerned about what are you actually delivering to the customer when you're doing a waterfall. During the requirements and design and coding phase, you typically have nothing workable. There's nothing ready to ship to a customer. There's very little to release to them, bar a beautiful suite of nicely written documents. So by the time you start getting into this iterative test fix phase, you begin to start getting a few more working features, but you're nowhere near releasing something generally. And here's a little thing I put up. So the new product waterfall, you got your 4 phases there, your plan, your build, your test, and your launch. The little guy in the boat there. How do we chart our entire course if we don't know what's ahead? So that's our planning and our designing analysis. The build, whatever happens, just keep paddling. Then your test, I wish we designed for this scenario up front. And then for the launch, patch it up as best we can, no time to change course now. So that's kind of, it's just a tongue-in-cheek of what the waterfall can be like. Waterfall has its place, and there are certainly definitely reasons as to why you should adopt waterfall, and we'll kind of look at a tiny bit of that. But in general, for newer product development, especially in the fast-paced mobile world and loads of different new kind of realms that apps are being delivered in, the waterfall isn't as suitable as it used to be. Another major issue, the relative cost of fixing defects in the waterfall. So in design, if there's a defect or a bug or something at design, it's just maybe you might just need to rewrite a couple of pages of the design. The implementation, it's 6.5 times more expensive to fix a bug in implementation than it is at design phase. In the testing phase, the development phase there. In the testing phase, it's 15 times more expensive to fix a bug than if you encountered it at the design phase. And when you get into maintenance, it's 100 times more expensive to fix something than it is in the design phase. I used to work for a company and we used to sell our base product at a loss. And the reason why was they had to sign a maintenance contract with us if they were buying our base product. So we would make our money. A lot of the money was made in the maintenance phase. And that was based on the waterfall model and how the waterfall model evolved. So the costs of fixing it at maintenance are quite high. But it does have its place. The waterfall does have a place. If you know your business requirements, without a shadow of a doubt, you know your business requirements and you know your technology solution, well then, you know, maybe waterfall is suitable and there's not much change in it. You know exactly what you're delivering. But agile, what we're looking at here for our module is this red phase here is where we're interested in. You kind of might know your business requirements. Some are unknown, some are known, but the technology solution, we're not fully sure what we're going to use yet. So, you know, we're in the unknown, halfway between known and unknown for both of them. So that's where the agile is sitting in comparison to the waterfall. And that's where agile is very suitable for as a development approach. So another little picture here. So waterfall process. This project has got so big, I'm not sure I'll be able to deliver it. So you're trying to deliver a big bang approach in your waterfall. Whereas in the agile process there, you can see that there's small little components in each of those, in the whole delivery. It's all comprised of smaller iterations. And the text under it is so much better delivering this project in bite-sized sections. So you're actually delivering those sections. So the customer is getting drip-fed the working application bit by bit throughout the agile process. So the cycles of work. So what it is an agile cycle of work. We often call them sprints. Feature A, a sprint. Feature B, a sprint. And they can be anything, depending on what you're building. They can be anything from 2 weeks to 4 weeks to 5 weeks. But what you're doing is you're looking at a reduced kind of waterfall in your sprint. So what you would have then is all of your features. You would be fully analysing, designing, constructing it, and etc., and testing it over time, and you would deliver each one of those blocks to the user. So it's like an iterative approach. So you'd have your vision you would start with your vision. So there would be some level of initial scoping. Exactly what is it we're building? What exactly do we want to build? So you are scoping your entire project and maybe outlining the suitable technologies, kind of a couple of your business requirements and so on, but nothing colossal, nothing in any way, shape or form the same as you would in your waterfall approach. But what you do is you'd maybe spec out iteration 1, what we might do is this, iteration 2, we might do this, and so on. And then it's like a mini waterfall in each of those iterations. It's like a mini waterfall going through there. So you would have an evaluation, you'd have detailed requirements, design and analysis, implementation and developer testing and so on, and then you would deploy it. So each of those iterations would be deployed to the customer. And that's what it would look like over time. Your working features is increasing the whole time as you are moving through this iterative approach, which are like mini waterfalls. You've got like working features ready to rock and roll, ready to go to the customer. But it's not just iterative, it's also what we call incremental. So you can see at the top there, the not like this with the big X through it. The first iteration is not usable, it's only a wheel. Second iteration is a chassis of some sort. Still not a usable method for, kind of transportation and so on. So these guys here, it's only by iteration 4 that you've actually got a working system. Whereas this is what we mean by incremental, that you've got some level of a working app. Yes, it mightn't do exactly what it is, the 100% that you need it to do, but you build it bit by bit by bit by bit. So, in this one you have it's moving. You can move it. It's a method of transportation, but it's primitive. This one you're building steering into it. This one you're building some sort of self-propelled mechanism maybe. This one you're adding the self-propelled stuff is now engine-based, and then you're building the car. So that's what we mean by incremental, that you're actually delivering a working part of the system every time that you're throwing it out to the user. Okay, and you can see the little smiley face are beginning to, he's beginning to get happier as the time goes on. Or he's not very happy up here. Yeah, he's only happy at the end. Okay. So waterfall versus agile. So we're interested in cost of change. We all know, we're software developers, we all know that change is going to happen. It will always happen. You can do your best planning, but it's always going to change. So when we're looking at this here, we can see the agile, change is welcome in agile to a degree, yeah. So over time you will, you can manage your change. As you can see, it's incremental. And it's also iterative. You can factor in change to a much better degree than in the traditional, because in the traditional waterfall approach, what we are doing is our design documents are done. So by the time we've moved into our coding and our testing, we would resist. It's normal to resist change at that stage because it's already been spec'd out and it's been built at the moment. So what we're going to look at then is, now that we have a handle on what agile is, particularly in comparison to the waterfall, we're going to look at the developer landscape. So over time, in the past 15, 20 years, the developer landscape has changed colossally. Okay, so there are literally new tools have dramatically eased mundane developer tasks. So there's automated test tools. That's what we're looking at today. We're going to look at JUnit. We're going to automate our testing because all developers know how much time you spent on testing. We're also going to start looking at system build tools as well. So we're going to look at Maven as the tool of choice. So we will start looking at that in probably week 6 of the notes. This is week 4. We'll start looking at that in week 6. What we mean by Maven is that we can get it to do a lot of stuff in the background that, when we compile any clips, we click the compile button. When we're testing, we do it manually. We will use Maven to kick off automated tests, build, package our stuff, package into jars. So we'll use Maven a lot. You got a little glimpse of it, I believe. Oh no, last week you got a little glimpse of it using the ASCII tables, didn't she? I think Eamon had you doing a slight bit of Maven. We'll also move into version control systems as well. So Git repos. So we've started getting you to commit stuff. So Git repos, we'll use any sort of Git repos. There's Bitbucket, there's GitHub, there's a lot of different ones out there for version controlling your software. And they are quite important when we start pushing stuff up to the cloud and doing, integrating stuff into cloud hosting solutions like Heroku and things like that, that they will use Git toolbelts. We'll also look at continuous integration and continuous delivery, which we'll discuss later on. I think we've enough going on at the moment. We'll discuss continuous integration and continuous delivery later on. But the OO languages, so we've chosen Java to do it with this. If you use those tools with an OO language, it can be so much easier to manage the development process. The cost curve is significantly flattened, so we're going to do that with Agile. We're going to try and reduce our cost curve so that we can accept change much easier. And as we know that upfront modeling becomes a liability, we will still have to do some speculative work. We'll still have to figure out, if you're adopting the Agile approach, you still have to figure out, well, what is it a mobile app? What are we dealing with? Is it a desktop app? What is it we're building? And also maybe get some business requirements of some sort, so we have an idea of exactly what it is that we are building. So there will be some speculative work. Maybe you'll also be laying out exactly how many iterations you're planning on doing, and maybe a couple of bullet points for each of those iterations to see, okay, well, in this one we'll build this, and this one we'll build that, and so on, so that you're still sticking to the incremental approach as well as the iterative approach. So test-driven development. So this is one of the agile tool sets that we're going to use. All code is guilty until proven innocent. We will automate this as much as we can. We will use automated testing tools to do as much testing for us as we possibly can. Good programmers write code, great programmers write tests. So give a guess what one we're looking for in our assignments. Great programmers write tests, isn't that right? So we'll be seeing hopefully a lot of testing coming in from you. The Martin Fowler, if ever you want to read about Agile, Martin Fowler is a really good guy to go to. He's a blog out there. He's really good. He's got great ideas and everything in the whole Agile area. He's like the father of Agile as well. He's got a lot of stuff out there. And he has said, never in the field of programming have so many owed so much to so developers of JUnit. So JUnit is the framework that we're going to use for testing, for automating our test-driven development. JUnit because it's Java unit. It's part of what we call the XUnit framework. There's, depending on the language that you use, there's a different letter in front of it. So the C unit is for testing C. This is what the mantra of test-driven development is. So what you do is, first off, you will write a test. It will fail. You won't write your code yet. You'll write your test first. It's test-driven development. It will fail because you haven't written the system yet. You haven't written your system under test. So it will fail. Then what we'll do is we will get it to go green. So it's red here, it's an error. Then we'll get it to go green by making the code work. We will write the code and the test will then pass, assuming that our code meets the test requirements. And then what we'll do is we will refactor, we will tidy it up. Now that we know that our code is working, make it more efficient, do whatever we need to do to adhere to, I don't know, business requirements and so on, kind of rules in the company as to how code is to be presented for going into production. We'll go into refactoring then. So your red-green refactor is generally the mantra for test-driven development. And you will write your testing first, and then you will write the code after it. So here's another, it's more broken down here. So you will start it. You will write a test that fails. You'll run the test and you'll watch it fail. It will fail because we haven't written our system yet. It's only in the green part that we start writing our actual code for the system. So this is the start. Red is where you start in your testing. It has to fail because the code's not written. We will implement enough to make our code pass. So maybe we might do if our test is saying like the return, when I call this method in the real system, it should return true. What we might do is just hard code a return true and our test will pass. So that's what we're doing in that case, is we are verifying that our test is actually correct. Then what we will do, we will start refactoring it in this section here, the green section. We'll start changing it so that we're actually writing the system under test, not just hard coding a dummy return true. And we'll write our code and we'll watch it pass. So in here we are actually writing our system under test here, which is the application that we're building. When we're happy that it is behaving, that the testing is working, everything is happy, we can then start refactoring for clarity. Maybe we'll tidy up our code. Maybe we've got naming standards we have to adhere to in the company for putting stuff into production, and just refactoring for efficiency. And once we've passed this refactoring phase, we'll run our tests again. They still should work. We shouldn't have broken anything. We will then check it in. So we'll check it into our version control system and push it up. So we put it up to GitHub, Bitbucket, whatever one our company is using. So test-driven development, it's a style of programming, which is 3 activities. Okay, coding, testing in the form of writing unit tests. So we look at writing unit tests, and then design in the form of refactoring. So the 3 things are all interwoven with each other. So what exactly is unit testing? So a unit test is a piece of code written by a developer that exercises a small specific area of functionality of the code being tested. So it usually exercises some part of a particular method in a particular context. So we will write unit tests for each of the classes that we are writing. And within our unit tests, we will have test methods exercising the methods that we've written in our class. So what we are doing is we are proving, unit tests are performed to prove that a piece of code does what the developer thinks it should do. So we'll test it, we'll do boundary testing, we'll do a lot of different types of testing in our unit tests. So the question then, yes, the developer, it's doing exactly what the developer thinks it should do, but the question remains open as to whether it's the right thing to do according to the customer or end user. So what that means is that that's a level of acceptance testing. So yes, it works perfectly from a developer perspective, and it's doing exactly what we think it should do as developers, but does it suit the business needs? Is it what the customer has asked for? And that's your acceptance test-driven development, behavior-driven development. Now, we're not going to look too much into that. We're only looking at the test-driven development, but you will see A, TDD, and BDD all over the place. So we're just flagging it to you here what that is, but we'll mainly focus on test-driven development at the moment, or for the module. So regression testing, this is really important part of writing any sort of a system that is in existence. So new code and changes to old code can affect the rest of the code base. So we all know that when you make a change to an existing code base, that any change that you make, it can break it. It may be in some further off reach of the system that it's broken it in, but it can break it. And it mightn't be immediately obvious to you that it's broken. It might be something that only rears its head a couple of weeks later after it's gone into production, that something is just not working right in one area of the system. So we all know that that can happen. So your new code and any sort of changes to an existing code base can break your code. So generally what you do when you do make changes is you rerun tests on the old code to verify it still works. And that's what we call regression testing. One of the main strengths of test-driven development is that whenever you write a piece of code, we will encourage you to have a test associated with it. So that when you do a regression test, all you have to do is kick off the automated tests and it will start flagging problems somewhere else. Something is broken, it will flag it to you. So regression testing is required for a stable, maintainable code base. So we do need to do regression testing. It's a huge part of development. And unit tests retain their value over time. And what I mean by that is that once you write a unit test, it's always available for your regression testing, be it 3 years later if the system is still in production. And it's a great way for others to prove that the software still works. We all know as well that when you write a piece of code, chances are that you're not going to be updating it, that somebody else will be coming along after you. So it's a great way as well. JUnit is a great way of having code tests or automated tests that any developer can go in and have can run and see. And they can definitely check if they are after breaking some code when they make changes by rerunning those tests. So what does unit testing accomplish? Does the code do what we expected it to do? Is it fulfilling our intent as a developer? Then the next point here is, does the code do what was expected all of the time? So disks get full, networks drop, and so on. Is it performing as expected? Is it, depending on how many records are coming in, is it having performance issues? Can the code be dependent on? We need to know its strengths, limitations, and we can do all of this in our unit testing. We can take many different approaches in unit testing and automate a lot of this. Does the test document the developer's intent? So an important side effect of unit testing is it helps communicate the code's intended use. So when we do write our tests, you can actually see it's a form of documentation for a developer. It improves what we call the DX, the developer experience, that you can actually go in and have a look at the unit test on any piece of Java code and see exactly, okay, well, that's what they're testing, and see what's happening here, and you can understand the code a lot easier. So test-driven development. So it's an iterative technique to develop software. You write the code. I know it sounds completely alien, but you write the tests before you write the code yourself. It's a practice that has to be learned, and it just takes a lot of time to get your head around it if you haven't been involved in test-driven development. It's as much about design as it is testing. TDD is part of design as well, and encourages design from the user's point of view and helps us to test our units in isolation. So if you have a massive system, a huge number of classes, chances are that your tests are going to be, you typically have a test for each class that you write. So chances are that your testing suite is going to be quite large. So sometimes it can take, to run the entire suite, it can take quite a significant amount of time to run it. So what you can do is you may run little portions of that suite, pick and choose what it is you want to run, and then maybe do a full system test at the end of the day when you're walking out the door. Just kick off the suite and come back in the next day, and it'll give you a report as to what's gone wrong. So our mantra now is code that isn't tested doesn't work. And code that isn't regression tested suffers from code rot. It will eventually break. So that's what we're going to adopt from here on in. So it's a documentation process as well. It is something that you have to learn and have to practice. It takes time to get to grips with it. The consequences, though, you will have fewer bugs. You'll have more maintainable code. You will have, so we'll talk about loosely coupled, highly cohesive systems when we start looking at solid principles later on in this module. So there's a bit of theory around that we will discuss. So during development, the program will always work. according to us, as in developers. It may not do everything that's required by the user, but what it does is doing it right. So how is unit testing carried out? First, you decide, well, what method is it that I'm testing? And then, so you decide how to test that method in question before you write the code itself. So you figure out, okay, well, that method should really, in this situation, return true, and in this other situation, should return false. So what we're looking at is the paths. We're checking the paths there to see if it is a Boolean value is being returned from a method as two possible values, and we will test both of those, both the scenarios that they can return those values in. So we'll decide how we're going to test the method. Then we'll write the code itself for the actual, what we call the system under test, the SUT. So we'll write that's the app you're working, that's Pacemaker. Sometimes you will write it concurrently with the implementation code. You'll write your test with the implementation code. It's as you're starting to get used to it, that's probably what you will be doing. And then you'll start maybe pulling back from writing your tests at the same time as your code and then doing your test first. Then you'll run the test itself and probably all other tests in the system. So these guys, whereas I was saying to you, this is going to be an automated thing that we're going to look at. JUnit is we're going to try and automate our testing. So we need to be able to see at a glance whether our tests are succeeding and failing. And that's why we're going to use the JUnit framework. It's very clear and very clear framework for telling us that we got it wrong, basically. And we look at that in the next slides. But some of the questions, a lot of people think, hold on, I'm writing a lot of code here for this app, and now you want me to write pretty much the same amount of code for tests as well. So there can be resistance towards test-driven development, but why bother with it? These are two really good reasons as to why bother with it. Significant reductions in defect rates, and that's proven. That this is empirical research. So it means somebody actually studied this. So it's at the cost of a moderate increase in initial developer effort. So yes, there is an initial developer effort in that, yeah, you have to write your test class, you have to write your code. So for, you're creating two files and you're kind of doing a lot more work from a keystroke perspective, you're writing a lot more code. But the reductions, if your system is going to be around for any length of time, the future reductions in defect rates is going to pay off. So generally the overheads are more than offset by a reduction in efforts in the project's final phases and in the maintenance. So then there's also anecdotal evidence. So anecdotal means that it hasn't been studied. It hasn't actually been undergone a proper field study, a field experiment or anything like that. Anecdotal means that it's just generally people's sentiment, what they feel, but it hasn't been studied, no statistics and things. So anecdotal evidence suggests that test-driven development leads to improved design qualities in the code and more general, a higher degree of technical quality. So it improves the code from the anecdotal evidence from people, developers reporting how they feel about it. Excuses for not engaging in test-driven development. I don't know, there's loads of these out there. You just have a read around the internet and you'll find them. Excuse number one, it takes too much time to write the tests. So as I was saying to you, it does, of course it does. It definitely will take more time to write your tests. You have to write your test and you have to write your class. But this is the single test phase where we have productivity, we're writing all of our coding, and then we go into a test phase. This is like the waterfall, the single test phase here. And our productivity shoots down while we get stuck in a whole test fix phase. So, but the pay as you go, as you write your code, as you go along, you maintain a pretty consistent linear productivity. It's not a curved line. So it's linear work. Yes, you are, of course, writing more code, but in the long run, it'll pay off. What you know that your code is working as you're checking it back in, you know it's working once you've written your code, your test right. So another excuse, no, I didn't get the testing done. The requirements were ambiguous. Okay, so why were you writing the code in the first place if you didn't know what you were actually supposed to be doing? And it comes back to, you still need to, even though it is agile development and we're not in a full waterfall life cycle, you still need to know exactly what your requirements are in order to write the code. Because what will happen here is if you don't know what your requirements are, you will then fail in your acceptance testing phase as well. The customer won't accept your product. So, and this brings us back to, remember I was talking to you about the behavior-driven development. So behavior-driven development is kind of like an added-on thing onto your test-driven development. And you can also write features for that as well. You can automate that as well using a lot of tools like Gherkin and stuff like that. But we're not going down that path at all. We're just going to concentrate on just the test-driven development cycle. Excuse number 3, it takes too long to run the tests. You can separate out your longer ones. So I'm going to show you later on, after the break, I'll just show you what we mean by the tests and what I mean by running tests. But you can actually choose which tests you want to run. So you can choose to not run your longer running tests and only run the short runs. Run the ones on the area of the system that you're currently working on. Yes, at the end of the day, as you're walking out the door, you can run your the full test suite as you're walking out the door, going home for the day, and you come back in the following morning and it'll tell you this didn't work, that didn't work, so you don't need to sit there and look at it. So, and you also, back to our thing here, your code isn't finished until you've verified it's worked. It's not the developer's job to test his or her code. Honestly, I did find these on the internet, right? An integral part of the developer's job is to create working code. It is our job. It is our job to make sure that our code is working. And it's with the rise of test-driven development, it is really pushed back onto us to make sure that our code is actually doing what it's saying it's doing. But it compiles. We all know this. We're all experienced programmers. A compiler's blessing is a pretty shallow compliment. So you've got a novice programmer up here and compiles, and I can't believe it worked first time. Compiler's blessing. Experienced programmer, can't believe it worked first time. He's all perplexed. Excuse number 6. We refactor our code so frequently that the time we invest in tests just isn't worth it. They are going to change and be irrelevant anyway. If you're refactoring your code so frequently, you most certainly need test-driven development. So how can you be certain you didn't break anything when you're refactoring your code? Refactoring and regression testing is definitely, if you're engaging in that a lot, of refactoring your code, regression testing is colossally important to you. So you need to make sure that, yes, whatever I change, it is actually still working. You can't be sure you didn't break anything further down the system in another subsystem or wherever it is. So regression testing is one of the #1 reasons for doing test-driven development. Good regression tests. So when we write our test suites, they will almost immediately show up any unintended side effects of our code change. And it will come up automatically. We will run our test suite and it'll come back and it'll tell us that broke. Yep. So a good rule is never refactor without tests. So that's not a good excuse at all. Like number 6 is not a good excuse. Number 7, we are such talented programmers, we don't need tests. Okay, you might be really good, but everybody has bugs in their code. We are human. And okay, you're writing the code. You may be an incredibly good programmer, but who's maintaining the code? Who's coming after you? Are you moving off the project? Who's going to be, are you on the project, staying on that project for the long term? So you got to think about in the future, somebody is going to be changing this code that you're writing, and you're going to still need regression tests for other programmers, maybe novice programmers coming in. So regardless, it doesn't matter how good a programmer you are, you still need to have your tests. Can we engage in test-driven development too much? Yeah, you can. Yep. So I understand that you're committed to test-driven development, but you think that testing the test your public methods and properties a bit too much. You can go a bit cracked on it. And what we'll do is we'll start looking at what we call code coverage and what's an acceptable code coverage. And there's tools out there to show you what code coverage is, and I'll tell you what code coverage is as well. So we'll look at that in the next set of slides. We'll have a brief look at exactly what is this JUnit. I've talked about it, but I haven't shown you it. So I'll have a look at what this JUnit is, and then I look at what we mean by code coverage. And we'll do it all through an example of just a small, tiny piece of code that you can play around with yourselves then to get to grips with it. Right, okay, so I will give you another little break again, and I'll be back in about 5 minutes. I'm just looking at the time there, so I'll be back in 5 minutes, so it's 20 past the hour now, 20 past 6 here. So I'll give you 5 minutes and then I'll come back. Okay, thank you. Bye.